G'day everyone, these set of videos are on vector functions, and what we've been talking up until now is with vectors we've been talking about something. You know, we've got if we've got our axes like that sort of thing, and we could have some position vector pointing to a point A. Okay, so that would be position vector OA if the origin is O. And that's good, and that's all helpful, and that's all nice. But what vectors are really good at is just also describing motion. So if you suppose I get a tennis ball or something like that, and I throw the tennis ball like that, and it lands on the ground down here somewhere. That's where it starts, and that's where it finishes up. What I can do is create a function of time, a vector function of time, which points to the ball's position at different times. So when time's equal to 0, the position vector might point to there. When time's equal to 1 second, it might point to that position there. That's where the ball is at 1 second. Here, that might be the position of the ball at 2 seconds, 3 seconds, and 4 seconds. And so what we've got is we can create these functions of time. So we've now got vectors which have a new variable what we put in that we call a parameter, and usually that parameter is t for time, and the position vector is changing with time, usually to describe the motion of a particle or an object. And so that's what we're talking about here. And so in general, these position vectors RT, something like that, and you'll get some function x of t in the I component, and you'll get some y function in the j component, okay, up and down. And if you're in three dimensionals, then you'll get some z function of t in the k direction. So you've got that sort of thing. And so just an example of what something might look like. So that might be x. I've already messed up. Sort of t squared I, so there's a function of t in the I direction, plus, let's go, sine t in the j direction, plus the square root of t. Okay, so in each component we've got motion. Okay, and so this tells you what happens to the particle in the left and right way. Okay, this tells you what's happening to the particle in the up and down plane. And this here tells you in the backwards and forwards plane in the 3 dimensions, what's happening in that. And so we've got this vector function that tells you the position of the particle at any given time. Hope that makes sense. That's what vector functions are. And what we want to know is to learn how to convert, or probably how to find is probably better, how to find a Cartesian path from a vector function. So that's what we're going to look at in this video. Okay, so how to find it. So what we've got is if you have some function like that we had in the last video, rt is equal to t squared I plus tj. Okay, so we've got something like that. What we want to do is have a look at this. Now, if you want to know what the path is, what does this thing look like, then you need to actually, we want to get rid of t, because we don't really care about time. If we just want to know what does the path look like, what's the shape of the path. So we just want to get rid of it. What we do is we want to eliminate t. And so the way to do this is we've got this x function of t here in front of the I. We've got this x function. So we've actually got the x is equal to t squared. That's the x function. We've also got that the y function up and down is equal to t. We've got that the y function there, it's just t. And what we can do is we want a Cartesian path, a Cartesian equation, which only involves x and t. And so we can do simultaneous equations with these guys and figure out something. So let's eliminate t here. So instead of having x equals t squared, I'm going to substitute in this value of y. Now y is equal to t, so x equals y squared. So the Cartesian y equals plus or minus square root. So what does that path look like? Well, hopefully it looks like this. Something like that. So that's the path of the particle. That's what it looks like. If you followed this along, that's the shape of the path that you'd get. So there you go. And that's what we're doing in these. So I'm going to go through a couple of examples, but what we're doing is trying to find that path. Now, just another thing, the domain of the path comes from, if you think about it, the domain of the path will come from the x function. So it'll actually come from the range of the x function. Okay, so you look at the x function, see what the range of that is, and that will determine what your domain of the path is. The range of the path, if you think about that, what are we talking about when we want the range of the path? We want the up and down. So where does that up and down information come from? That comes from the range of the y function. So in this just example that we've just done now, here the range of the x function is 0 to infinity, so r positive. Well, no, it's not r positive because you have 0 as well. So in this fact, the domain for this one will be from 0 to infinity, because that is the range of this x function here. What's the range of the y function? Well, it's all r. So that's how we do that. Let's do some proper examples, and let's just do that. So let's say we have some r function. This is just our position vector function, equals, let's go 2ti plus 6t plus 1j. There's our r function, our position function. We want to pull out the Cartesian equation from this. So let's go. Firstly, we want to write what is the function of t in the left and right. In other words, what's our x function? Our x function is equal to 2t. That's there. Also, our y function, our up and down function, is 6t plus 1. Now, all we need to do is eliminate t, so you could, find out what t is equal to here and put it into this equation. I'm just going to take a short little step here. If x is equal to 2t, y is equal to 3 times x, in other words 3 times 2t plus 1. And so there we have it. There is our equation of the path. So the particle is going to move in something like that. If that's 1 there, it's a pretty bad diagram. But if that's 1, in fact, I don't like that. It's going to be steeper. Let's go 1 there. It's going to be sort of steeper than that. 1 there. That's what the path of the particle is going to look like. And if you wanted to find out, well, which direction is it travelling, that sort of thing, you could just find some values. You can put in at time 0. Where is it when time's equal to 0? When time's equal to 0, let's just do it. Just have a look. R of 0 is equal to 0i plus 1j. So in fact, this point here is where it starts. Alright, which direction does it go? Let's have a look. R of 1. At times equal to 1, we get 2i plus, what did I say? Times equal to 1, so plus 7j. Okay? So when time's equal to 1, it's up in this direction. In other words, the particle is moving from here upwards like that. How do we, where would it end up down here? That would be if time was negative, so negative time down here. In this question, we weren't told that time's greater than 0 or anything like that, so that's fine, that's the entire line. If we did see that time was greater than or equal to 0, it would start here and move forward, so it would look like that. Okay, so there's our first example. Hope that makes sense. Let's get on to something a little bit more complicated. Let's have a look at a bit more of a nasty one. 3 sec lambda in the I direction plus 2 tan lambda in the j direction. Cool, let's have a look at this. Firstly, the first thing you do when you're trying to find the Cartesian path is just to write down what is happening in the x direction. Well, it's 3 sec lambda. What's happening in the y direction? In the y direction, we've got 2 tan lambda. Now we need to find something so that we can eliminate lambda. And often Pythagorean identities will help in these situations. So you remember that sine squared plus cos squared is equal to 1. Well, that doesn't help, but there is one that connects sec and tan. Okay, so if we want to divide those by cos, and they're all cos squared, what we get is tan squared plus 1 is equal to sec squared. So this is good. We can use that here. So let's just rearrange this a little bit. So we've got x over 3 equals sec lambda, and we've got y over 2 is equal to tan lambda. And we know that tan squared, we'll put lambda in here, lambda plus 1 is equal to sec squared lambda, so it doesn't matter what lambda is, this or x or whatever this variable is, doesn't matter, this always holds. Therefore, what have we got? Right, what's tan squared lambda? Well, that's this squared, so that's y over 2 squared, that's that part there, plus 1 is equal to sec squared lambda. Well, sec lambda is that, so it's x over 3 squared. Beauty. And now we can just rearrange this. Therefore, x over 3 squared minus y over 2 squared is equal to 1. Clean it up just so it's something that we're more familiar with. X squared over 9 minus y squared over 4 is equal to 1. And there is your Cartesian equation. That's the path of this particular particle. What is that? Hopefully you know by now that that is a hyperbola. Okay, so it's a hyperbola with asymptotes of b over a, so 2 over 3x, y equals plus or minus, so it looks like this. Crosses at a is equal to 3, so it goes 3, negative 3, so we get something like this. It's an east and west, so that's the path of the particle. It comes down here and then goes up here like that, and it continues in that. So that's the path of that particle. Cool. Let's do one more. Let's put a restriction on our values for this one. Okay, so RT is equal to 2 cos t plus 3 sine t. And let's restrict t here to 0 to pi on 2. Let's just make it a bit more interesting, see what happens. Okay, let's do it. First step, always the same. X, I tried to make that red. How many times of video do I say that? 2 cos t. Y is equal to 3 sine t. I forgot my i's and j's, you didn't tell me. I there, j there, sorry. Good. So therefore, x over 2 equals cos t, and y over 3, this looks familiar, equals sine t. Good. And we also know that cos squared t plus sine squared t is equal to 1, our Pythagorean identity. So, therefore, we have cos squared t is x over 2 squared, plus sine squared t is y over 3 squared, and that's equal to 1. Clean it up so it's something that we recognise. X squared over 4 plus y squared over 9 is equal to 1. Okay, now what is that shape? Oh man, that's terrible. What is that shape? What have we got? It's an ellipse. Its radius in the x direction is 2. So I'll put that there, 2. And its radius in the y direction is 3. So it looks something like this. That is terrible. It's easier for you to do than me. So it looks like that. Or does it? Now, remember we've got a restriction on t here. So we need to find, actually, to be able to find out what the true sketch of the path is, we need to look at the domain and range of our x function and our y function. What's the domain and range of these guys? So let's have a quick look at it. So for x, let's have a look at the x. Remember, the x function will tell us our domain. So let me just do a quick sketch of x equals 2 cos t. So that'll start up here and sort of go like that. So that's up at 2, and there's pi onto there. Okay. So what's the range of this function? Well, in this region here, that's what we're talking about there, the range is between 0 and 2. So the domain of our path will be between 0 and 2 inclusive. Okay, so there's our domain. I'll do my range over here. The range comes from the range of the y function. So let's do a quick sketch of the y function. Y equals 3 sine t, so that goes something like this, and it goes up to 3. Pi on 2 is there, and so what we're talking about is that section in there. What's the range of values that you get between 0 and pi on 2 for t? We get the range will be between 0 and 3. So how does that apply to our sketch of the path? Well, it does not include this entire red line of the ellipse. We need to actually erase that. Oh, I can't erase that, but the red is not correct. The green that I'm about to do is actually correct. What will this look like if we only have a domain from 0 to 2? That takes out this entire negative side here. We're only going to talk about this up here. But my range is only from 0 to 3. So in fact, my line will end up looking like just this quarter of the ellipse, like this. So it's only that. And that's it. So that there is the answer, the solution. Not the entire red thing. So just be really careful when there's a restriction on the domain of t, then you need to make sure whether it's the whole path or just part of the path, that sort of thing. So that's vector functions. Enjoy.